Yes, exactly. Montague.
Did you bring your printed phase diagram?
That's right. No one heard you. All right, that's great. So here we are. No one was paying attention to the questions from the gallery, peanut gallery. So we talked about this. We did the PV exhaustively last time. Now we're going to go to the PT phase diagram. We have A, B, and C, and we have A, B, and C on here. A, B, and C going up. So these are the same tracks we saw in the PV phase diagram, but in the PT phase diagram. So you should be able to go and compare those paths A, B, and C in both diagrams. Okay. Now, if you're given this phase diagram without any labels at all, the axes will be labeled. You should be able to identify all of the parts. Okay. And once again, where do you get started on this one? Same kind of thing for me. I go to the gas region, a really high temperature, low pressure, because that'd be an ideal gas range. Would be low pressure and a high temperature, way above its critical temperature, and that would be the gas. And so then if we cool it down really low temperature, you're going to have the solid, and then liquids in between those two. So solid, liquid, gas, pretty easy. Then these lines are the equilibrium lines. And so they if you're taking a solid and you warm it up, it's going to sublime if you're below the triple point, and it's just going to sit there at equilibrium with its vapor, and until all the solid's gone, and then you're going to heat up the gas. Solid, liquid, if it's above the triple point, it'll melt at that vertical line, and it'll sit there until it all melts, and then it will continue on, and it'll boil, and it'll sit there until it's all boiled away, and then you're just heating the gas. And then D, this is kind of an interesting one. That's an isotherm. And in this particular case, we're starting at the top in the solid region, and we're just dropping the pressure, but we're keeping the temperature the same. And so there'll be a certain place at which the pressure drops and that solid can melt and become a liquid. And then there's a place where that liquid can boil and can become a gas. So we've dropped the pressure until the liquid boils. Do we ever do that? Yes, we're doing that in my lab now. I bought a little vacuum chamber, and we're doing a certain type of cleaning called vacuum cycle nucleation. So we're sitting at liquid water, and we have our little sample under the liquid water, and we have it hooked to a vacuum pump, and we turn on the vacuum, and the pressure drops. And eventually, it boils. It boils at the vapor pressure of that water at that temperature. And so it'll drop down, and the water will just start to boil. And so how is it that it's boiling? I mean, what's going on? Well, there are hot molecules in that liquid that have a certain vapor pressure, and they will leave that liquid, and it leaves behind the cold molecules. And so if we do this long enough, which we pull all the hot molecules out and into the vacuum pump, then the liquid should be cold. And you can actually freeze it. So you could pull enough vacuum on this that you would pull all of the hot molecules out and actually have only molecules that are below freezing. And if you bring that back up to 1 atmosphere, you'll have a little chunk of ice left behind. It's kind of cool.
So it's not the same temperature then?
What's that?
It's not the same temperature.
Yeah, so what we're doing is not an equilibrium situation because we're pumping away the vapor. And so we're actually taking that vapor out. If you were to hold it and keep that vapor in there, then you'd be at this equilibrium spot. Yeah. And if you tried to pull the pressure down any further than that, eventually you could if you got it all into the gas phase. So that would be like, again, a piston where you increase the volume up to where now that same amount that was a solid would occupy a liquid, and then it would occupy the volume of the vapor at that particular temperature. So this is the experimental phase diagram for CO2. So let's expand this a little bit. This is from the Atkins book, an older copy. But notice the y-axis is broken. It's down here, it goes from 1 to 5 atmospheres. You see the marks. And then it's 67 and 72. So there's this break in the middle of the chart, and so you have, this go up to the critical point, and you have 304 degrees as the critical temperature for CO2 and 72 atmospheres for the pressure. Here's 298. So you should be able to read these phase diagrams. If you didn't have any of the labels in the middle, but you had all the numbers, you should be able to tell me what the vapor pressure of CO2 would be at room temperature using this particular phase diagram. So here we are at room temperature, and you come up here and you see the liquid gas equilibrium line, and you come across at 67 atmospheres. So that's going to be the vapor pressure of liquid CO2 in equilibrium with its gas phase at room temperature. We had this crazy PChem professor at Oregon State, and he liked to do demonstrations in class, but he was a theoretical chemist, like purely like pencil and paper theoretical chemist. He did statistical mechanics on different kinds of polymer solutions and so on. And so his classroom demos were always a wreck. And he had the machinist make this plexiglass tube of a really thick plexiglass tube with the screw-in end caps, and he dropped some dry ice in there and capped it off. And yeah, and he was going to hopefully show liquid CO2 at room temperature. But this plastic had to hold 67 atmospheres. Okay. Now the machinist said, I mean, it was pretty thick, maybe half-inch thick plexiglass or polycarbonate. I don't exactly know what the material was. But he dropped the dry ice in there, but it as it was subliming, it was cooling down the glass, the plastic, and the plastic got brittle and it started to crack, like during lecture. Yeah. And so he's sitting there, he's showing this, and he sees it start to crack, and he was like, everybody out of the room. And so they like all the students grabbed their books and bags and ran out of the room, and he stuck it in the drawer or something. And so I ran with the students. I was his TA, so I got out of there too, and never knew what happened to it. I don't think it blew up, but I was nervous too. Yeah, so he was a blast, Dr. Evans. And he also did a deal with mercury oxide turning into mercury. You heat it up and it decomposes, right? Have you ever seen this? But not a demo you want to do in class, because you've got mercury. You're going to make liquid mercury, and it's going to be over a Bunsen burner, And so he takes red mercuric oxide, and he's heating it over a Bunsen burner, and the oxygen leaves, it decomposes and leaves behind liquid mercury that's now being heated, and so the vapor pressure is going to be too high. And so he's like starting to get nervous. There's a big old Bunsen burner, and he starts tapping the test tube on the Bunsen burner and breaks the bottom of the test tube, and all the mercury oxide flows down into the Bunsen burner. He's like, everybody leave. So we ran out of class again. Those are my two favorite Glenn Evans stories. He's fantastic. One of my heroes. But
If we go back, like, I get that there's a break in the y-axis, but there isn't in the x-axis, and the x-axis isn't calibrated. Is it just a thing for phase diagrams that it doesn't have to be, like, well calibrated?
what do you mean, just because it doesn't look linear?
It goes from 298 to 304, and that's a huge, like...
Yeah, huge gap, but it's only 6 degrees. Yeah, I see what you're saying. And this is 16 to 298. That's a big gap. So yeah, it doesn't. Yeah. So it doesn't look like this axis is necessarily linear. Yeah. Well, I mean, to display what this is displaying, like room temperature is an interesting point, and so they just draw it up here. Here's 1 atmosphere. It doesn't even really hit the blue line. It should hit the blue line. So, I don't want to brag, but I could probably make a better figure than this. So I see your point, and I agree with you. It's not a great x-axis either. Yeah. And then this is the triple point, the 5.11 atmospheres and 216.8 Kelvin. That would be the place where all 3 phases are in equilibrium. And that would be hopefully what, if that plexiglass thing had held, and if it cooled down to 216, we'd have solid, liquid, and gas all in equilibrium inside that plexiglass thing. And we'll see it. for CO2. Now here's water. Okay, this one may have the same similar problems, but it looks a little bit more promising. We have 200, 300, 400, etc. We have vapor here. We have 1 atmosphere, so this is the normal freezing point or melting point. Here's the normal boiling point. So 373.15, 273.16 is the triple point. 273.15 is the melting point, so they're very close to each other. That triple point pressure is 0.006 atmospheres. But this also has a break. Now we go from 2 to 2,000, 4,000, 6,000, 8,000. And so what more could there be? We have solid, liquid, gas. But think about the solid. You can have a lot of different crystal structures. And so this one's kind of crazy. We have ice 1, ice 2, ice 3, ice 5, ice 6, and then there's a bunch of others up there. Yeah. And so then there was some controversy over, like they thought there was an ice 4, and then they published ice 5 and ice 6, and then later there was a paper that came out that said that ice 4 was really ice 3 or ice 5, and so ice 4 disappeared. Like they said, well, that was a misidentification. There really wasn't an ice 4, and now it's one of these others. So they just pulled ice 4 off the phase diagram, and so again, you see this conversation that happens in the literature, and you end up with crazy results because to go back and relabel things would confuse people even more. So to leave ice 4 as sort of this periodic discovery that then got, corrected to say, well, it's really mislabeled. What they discovered was ice 3 or ice 5. And so you'd have to find those papers to kind of decipher all of this. It would be easier than having 2 designations for ice 5 and 6 and 7 and all the ones above it. They would be off by 1 number, and you have to figure out what dates those labels applied, and that would be confusing. So, but what's interesting is look at the slope of this line here. It's positive, which means that you could have solid ice, theoretically, above the boiling temperature. It's weird, isn't it? So yeah, could you have solid ice above 373? Well, it depends on the pressure, right? If you're up to millions of atmospheres, you're not letting it boil. Okay, so you could heat that solid up above its boiling point at room temperature, or boiling point at 1 atmosphere.
Would pressure that high actually exists outside of a lab?
Well, maybe if you're down at the bottom of the clouds of Jupiter, something like that, you might have ice in a certain phase that's solid because of the enormous pressure, but it's also at an elevated temperature. And so it's, they think, I don't know, that they dropped some probes down into the clouds of Jupiter, and we're getting data. I haven't looked at the results, I wouldn't know, but they did say, it probably sank until it got crushed because the pressure goes up and up and up, and then it just gets crunched. But I don't know what information they got out of it. But yeah, that might be a scenario where you could have solid ice that is at a really high temperature. It's just fun to think about. That's my main point. Yeah. And notice the slope of this line goes up. It's kind of a logarithmic change, and then it changes dramatically because we've got this change in y-axis. So that's not real, this effect where it takes that sharp turn. That's just because we've changed the scale of the y-axis. So we've looked at the PT phase diagram, and then the last set of notes we looked at the PV phase diagram. And this was the greatest thing since sliced bread. Okay, when I saw this figure in the text, I went crazy. And this was actually in a different text, Engel and Reed. It was one of the reasons why I switched to that book for a while, because they opened my eyes as to how the PV and PT charts were related. This is a 3-dimensional shape that is incorporating both the PT phase diagram and the PV phase diagram. And so this is what Matt was asking about. This is the 3D shape. So pass this around.
I think you should print one for everybody here.
I think you should babysit the printer while it gets this far and fails. But yes, I would certainly do that, but I don't have time to babysit.
Did you change the filament yet?
I think I went back to ABS. So this might print a little better with ABS, I don't know. Here. So this is the PT phase diagram. Do you see it? Okay, and this is for water. And this is the PV phase diagram. Yeah. I have tried to draw the lines. And this little line this is for water, so this little line is supposed to represent 1 atmosphere. Okay, so looking at it this way, that's the 1 atmosphere line. So there's the boiling point, there's the freezing point. Pass that around. I would love to print one for everybody, but 3D printing is not a set it and forget it exercise. You know, if it goes well, yes, it does. You set it and forget it. But it separates from the bed. It makes a bird's nest, a filament. You go in and what your print looks good for about an hour, and then 15 minutes after you leave, just like Gaussian, everything goes berserk, right? And you come back and you've got half of an object and a bird's nest on top. Yeah, and it smells like burnt plastic. So this is a very complicated phase diagram, but you should be able to walk through all of these paths. The line drawn on there for 1 atmosphere is like A to B to C, D, E, F. Okay. So let's walk along here. Now this one on the screen is similar to the CO2 phase diagram. The one I've printed for you is water. We'll talk about, let's go back to water right here. Look at water. This slope of this line is really strange in that it's got a negative slope. Okay, that means that the solid is more dense. Less dense than the liquid. Okay, you raise the temperature. You raise the pressure and you're in the liquid region. You drop the pressure and you're in the solid region. That's not normal. Normal meaning most abundant. Okay, all other substances have a positive slope for the solid-liquid equilibrium line. Water has a negative slope. This means also that ice is less dense than water and it floats. The other solids are going to sink in their liquids. Okay, so liquid CO2 would be on top of the solid CO2. Liquid water is below ice. Okay, this also has been essential for soil production on our planet. Because when water freezes, it breaks open the rocks and busts up the little bits. And so weathering of rocks depends upon this phase diagram, okay, and the unique properties of water. So what you have in your hands kicking around, that solid liquid equilibrium line has a negative slope. You see that? And then you can also see the volume change for the solid and the liquid. You see how the solid is got a larger volume than the liquid? It kind of goes inside that little shelf. And so when you're looking at the PV, you can't see that shelf really because it's a negative surface. You follow what I'm saying, Christian? Yeah. Yeah. So the solid has got a larger volume than the liquid. So we could also look at these where we're dropping the pressure on an isotherm. So again, here's temperature. So all of these red lines going this way are isotherms. Okay, here's volume. So a line that was going to slice this way would be an isocore, yes. And then the line that goes straight across on this axis would be an isobar. Okay. All right. There's one more that we haven't covered, but it only applies to mixtures. Since this is all a pure substance, we can't show an isopleth. Okay, but plethora is an amount. And so later on when we get to mixture phase diagrams, we'll talk about isopleths. And that's one of your vocabulary words that I put on the list. Okay. Now, many of you remember from your thermodynamics class when you were doing cycle problems, the Carnot cycle, which was all in gases, and it was an adiabatic expansion and compression and an isothermal expansion and compression. And so zooming in here, this is the Carnot cycle up in the gas region. And so you had isothermal expansion, adiabatic expansion goes downhill, a little steeper path, isothermal compression, and then adiabatic compression goes up the steep hill. And so you have isotherm, adiabat, isotherm, adiabat, and I've drawn that on the phase diagram as well. That's really the main part. So let me, how much time do we have? 9:22. I just want to make sure that y'all are comfortable with any of these paths in here. Okay? So I don't know how we want to do this, but let me just start us on a path. So one person tell me what's happening at A. So Haley, why don't you tell me what's describe point A? Like what phase is it?
Solid.
Yes, solid. Okay. So Celicia, tell me when I go from A to B, what's changed?
It's at the point where it starts melting
Where?
at B.
At B, okay. But just the path from A to B. What's changed from A to B? It's all solid. And temperature's increasing. Has the pressure, has the volume increased? We've increased the temperature. We've stayed at the same pressure.
Has the volume increased? No.
It's hard to see from that diagram, but it has a little bit. It has a little bit.
The very top of the three-dimensional structure got
Oh,
kind
it
of
goes
spreads out.
up, yeah.
It moves a little bit. This would be the more drastic. Yeah, this would show the change. It's more drastic up here than it is down here. But yeah, the volume increases a little bit. And that would be that volumetric expansion with temperature of the solid.
Still hard to
Not a
believe
lot.
solid.
Yeah, so solid changing temperature is going to expand a little bit. Okay. And then Madhuri, what's going on from B to C? Yeah, so the solid's melting. So it's staying at that melting point. So this is straight across on this melting isotherm. So the volume's changing because the liquid, in this particular case, the liquid is a higher volume. It's less dense than the solid. Okay. Everybody look at this here. Notice how this is like on the inside. Okay. So the liquid is a smaller volume than the solid. So when it melts, it goes this way to the liquid. The liquid is at a smaller volume than the solid. So for water, when it melts, okay, the less dense solid becomes a more dense liquid. So the ice stays at the top and just melts at the top of the container. Whereas in this one, the liquid is less dense. See the volume axis? Same mass, different volume. So because the liquid has a bigger volume, the liquid is less dense. In water, the liquid has a smaller volume, more dense. Yeah. Okay. Everybody comfortable with that? The melting behavior, this is water with this sort of inside lip. That's other substances with the lip that goes that way. I'll pass this around again if you want to look at that. And I agree, man. I'd love for everybody to have one. You know. Can I make them smaller, maybe? It'll be, yeah, like we'll hang it from your rearview mirror.
An ornament on the Christmas tree.
That's right, exactly. Yeah, that's right. We had bumper stickers and now ornaments. This is great. Preston's good. Yeah, that's right. Okay, so then Jerome, what's going from C to D? So C, we're
You're increasing temperature, your volume's changing very slightly too.
Yeah.
And the pressure's the same.
Pressure's the same, yeah. Temperature's increasing. We're just heating up the liquid.
Now you approach the liquid gas.
Yeah, so we've and his expanded a little bit because again the liquid will expand when you heat it. And all right, and then the Shini, what's going from D to E?
Temperature stays the same.
Mm-hmm. And what temperature is that? What do we call that temperature?
DC.
But look at the phases that are.
Bed press.
Yeah, so boiling. Yeah, that'd be the boiling temperature. Yeah. Well, it's kind of we're looking at it at a tilted angle. If we were to line it up, the pressure would be straight across. So we're walking along an isobar. Yeah, so the pressure's the same. Yeah, volume increases greatly. So we're turning it from a liquid to a gas at the boiling temperature and at the boiling pressure. So pressure and temperature stay the same, but volume changes dramatically. Yeah. And then let's go to next meaning, E to F.
Temperature is rising
Mm-hmm.
and volume is slightly increasing.
Is increasing, yes.
Yeah, liquid phase to gas. Yeah,
We've already done the liquid phase to gas from D to E.
yeah,
And so at E, we're all gas.
yeah.
So E to F, yeah, we're just heating up the gas, right? And it's expanding because you heat a gas, it expands more than the liquid expands or the solid expands. So the slope on that line should be bigger. And we'll see that in the little orange thing. We see the gas change with temperature is quite large. Although we really can't see it very much on here, but that E to F tilts that way a lot more, because the coefficient of thermal expansion for a gas is bigger, about 1,000 or 100 times bigger than the solid or the liquid. Solids and liquids are maybe the same order of magnitude or maybe one order of magnitude different. But then when you go to the gas, the expansion of a gas with temperature is quite large. Audrey? No, so this red line I'm walking along is an isobar. So it's this line right here. So see that A, B, C, D, E, F here matches F there. So that's an isobar that we're walking along.
I like how the triple point turns into a triple line.
Yeah.
Vertical.
That was a really interesting thing, is that triple point here. We're looking straight down this line. Like, see, I get right here and the line disappears.
Yeah.
I'm looking straight down that line. And so, if I look at the PV phase diagram, I can see this sort of face right here that's the liquid gas equilibrium, and this shelf here that's the solid liquid equilibrium. But if I'm looking down the side, that face of the liquid gas is just that sideways line up here. And then this shelf here, I'm just looking at the side of that shelf right there. Isn't that great? Oh, come on.
Think about the kind of supercritical stuff we have.
Yeah.
The fact that it kind of sloped off to the gas.
Yeah, it gets up there, and then you have this really steep slope in the supercritical region. Now, in that diagram, I don't know if it's that accurate, but this isotherm that goes through the critical point, there's kind of a dramatic change in slope right here on the 3D printed piece, and I don't know if it's that abrupt. I just don't know. Look at the supercritical region. It's perfect that you have it in your hands because you've been asking the most questions about the supercritical region. There's this dramatic change in slope up here on that isotherm that goes through the critical point. You see that? I don't know if that's real. It may be. I don't know who produced this. I didn't make this object. That's the beautiful thing about our internet and the 3D printers now. It's called Thingiverse. You ever see Thingiverse? Like universe, only it's the universe of things. Okay? So you go on to Thingiverse. Like you want to make a phone case with your name on it. Okay? You go to Thingiverse and you type in phone case, modifiable phone case or whatever, and you'll get these little printable object files, and you might be able to modify them and like put your name in there and generate this 3D printable file that you then go to my 3D printer and hit print, and it prints it for you. So you just download the object and print it. Isn't that strange? But how useful is that, right? So the person that designs it doesn't need to be in Huntsville. The person that designed it could be in anywhere. Could be on a different planet. Okay.
This is really cool.
It's very cool. The other thing that's cool is they thought about this and thought, different planet. Maybe that's interesting. Maybe we could put people that are on the space station, maybe instead of give them backup tools and backup objects, we just put a bunch of 3D printers on the space station, and when something breaks, we're like, all right, print one.
They aren't doing that.
And they are doing that. Yeah, they have metal 3D printers, and so they break a wrench, they print a wrench. Isn't that cool? And so then they just take up the raw materials, the metal powder, and then they print what they need. Yeah. And, you know, we're printing food.
There's also a
Yeah. So you want to make a wedding cake, and it has a beautiful thing for the bride and her initials and his initials and everything like that with all the birds and stuff like that. Or maybe you're into Harry Potter and you want the little Deathly Hallows thing or whatever. You know, it doesn't matter what you want. You make up the file and it'll print in chocolate.
That's pretty good.
Yeah, that's super easy to do because chocolate has a low melting point and flows beautifully. And so they have chocolate 3D printers.
They printed a bridge over in Europe.
Really? Yeah, and there's a guy that printed like a castle type house but with concrete. So he's got this big thing that pushes the concrete around. It prints. And it's pretty neat, yeah. So this is pretty cool. Thingiverse is a place. There's lots of other things. And then Tinkercad. If you want to get into this, Tinkercad's probably the nice entry-level builder. And so Tinkercad and Thingiverse. And my 3D printer's just sitting there. If this is something you want to play with, certainly you can do that. Yeah.
It's fun.
Yeah, I've printed some things for the lab, you know, little holders. Like if you want a vial holder that holds a vial just so, and maybe for your phone to take pictures of your vials or something, then come by, we'll print it up. Yeah. Okay, let's do one more isotherm and then we'll call it a quit. Okay,
Let's do
a
the
couple of isotherms.
pH.
Yeah, so let's go up here. Yeah, so let's see. So Chamari, what's going on at G?
Same temperature, but volume increases.
Yeah, what phase are we in at G? Yes, it's gas. Yeah, that's right. And so let me go ahead. So we'll stay at the same temperature, and we'll compress it. So we have a piston. So we start compressing it. We change the volume. So G to H is compression, isothermal compression. Okay. So what happens at H, Sarka?
It's liquid and gas.
Pardon?
Liquid and gas.
Yes, at H to I, yeah. So what's going on?
Temperature
Mhm.
and volume decreases.
Mm-hmm. Why is the pressure not changing? So we're changing the volume. We're not changing the temperature, and the volume's changing, but the pressure's not changing. That's interesting. So we're able to squeeze it into a smaller space, but we don't have to change the pressure to do that. So remember, we have 4 state variables: pressure, temperature, volume, and number of moles or phase, moles in each phase. And so what we're doing, we're changing the volume, but pressure and temperature are constant, so something's got to give. And what's giving is the phase of those moles. It's going from gas to liquid. So we're condensing. So condensation, H to I is condensation. I to H is boiling, but H to I is condensation. So we're able to squeeze on it, the pressure doesn't change, temperature doesn't change, but eventually we hit at I, it's all liquid. So what's going on from I to J, Matthew? I to K, sorry, I jumped. There's no J, that's true. I just assumed it would be alphabetical, but
I thought you were giving me a trick question.
it's not within the, not out of the question.
There is a steep increase in pressure because you're all liquid,
Mm-hmm.
moving toward the solid. liquid line,
Mm-hmm.
so pressure is increasing dramatically.
Mm-hmm.
It's difficult to compress.
Yeah, so you're compressing, so you're still pushing on that
Volume's
piston.
changing.
The volume's changing. Yeah.
Slight, and for that
Yeah.
slight change, you need more
Yeah,
pressure.
so the rise over run is that slope, very small run, very small change in volume creates a huge change in pressure. So you have a dramatically steep curve there. Okay, Will, what's going on from K to L?
Your liquid is starting to become solid, so
Mhm.
it's freezing.
Yeah. So you're freezing it out by pressure. It's kind of a strange phenomenon, but you're pushing on it, and that liquid is starting to crystallize or freeze out. Yeah.
Is it always considered freezing out as far as even no matter the temperature for a liquid to go to solid, or is it?
Yeah, I think so. Or fusion.
Fusion.
Yeah. So it's the phenomenon of fusion. But I almost never use fusion, even though I know that's the technical term for that, because it's confusing. You're dealing with like nuclear fusion now. That's the more common use of fusion.
Because
Oh.
like the
Yeah.
first sublimation would be fusion versus plus.
Yeah.
rotation, so-
So that's K to L. Okay, Christian, what's L to M?
From L to M, it's going from liquid to a solid.
Will, K to L. Go back to Will. What happened from K to L, Will?
It's freezing, so from liquid to a solid. So
Yeah.
L should be completely already a solid.
So it's all solid at L.
Okay, L is that solid.
Yeah.
And the pressure is increasing and the volume is decreasing.
Yeah, so you're still compressing it a little bit. So again, it's a steeper slope. The volume changes even less, and now the pressure is really steep. So it's an enormous amount of pressure to compress it. But you can do that. Solids are compressible to some degree. This is really important, this compressibility of the solid in subsea petroleum engineering. Because my brother-in-law is a subsea engineer, and they make these, control objects. They're called Christmas trees. On land, it looks like a Christmas tree, kind of. You've got the wellhead. This bolts onto the wellhead, and you got a valve that goes to the pipeline, a valve that goes to the test thing, and you've got other kinds of valves, and you got all these valves and things that come off. And so if you look at it, it's like got limbs and a stick. So it's a Christmas tree. But down below the surface, like subsea, it just looks like a box with a bunch of holes in it and then a pipe that comes out. But they still call it a Christmas tree. They still call it a tree. He has completed wells at greater than 5,000 feet water depth. And so you can calculate the kind of pressures that 5,000 feet of seawater would put on your metal. And it does compress steel. Like it's squeezing the steel, so the dimensions change. You build it on land, and when it gets down to the subsea, the dimensions change of these objects. So these engineers have figured out we got to build it bigger than we need it. And they use the engineering calculations for what's going to happen to that steel. Over here in the solid region, when it's under that kind of pressure, what's the new dimension going to be? And that's the dimension we need to aim for. So they build it differently than it will be when it's installed. Isn't that amazing? They actually change the gasket seating surfaces and everything. There has to be precision, construction down at the ocean floor. Well, they can't adjust it down there. They have to build it and then take into account the compression from the seawater that's going to cause it to do its thing.
Think about your different materials that you're using. You take the steel down, you have gasket. You get
Yeah.
down there, your steel compresses a little bit, but your gasket compresses a lot, and now you're not even sealing.
Exactly. That, and then they have even rubber gaskets too, and those change a lot. Yeah.
That's a nice effect.
Yeah. Which question? From L to M? Yeah, L to M. So it's still an isotherm, so it's still the same temperature, but volume changes a little bit, pressure changes a lot.
So explain to us what's going on from M to infinity.
If we get to infinity, you have fusion.
Usually-
Real fusion. So that the nuclei are crushed together and the electrons squeeze out. And then, yeah, so eventually it explodes. Yeah.
For clarification, on the mixed plot and then the PVT plot, is M offset?
No, if we look at this, yeah, so let's go. What we just did was from G to M. And so here's G to M. And so G was gas,
Oh,
gas liquid, liquid, liquid solid right there. That was yours. And then Christian ended up with going from solid to more pressured
I
solid.
was looking at the two different red lines.
Okay.
Okay, it does, yeah.
Yeah. Very good. And then over here, let's just go around again. So Haley, N to O. Yeah, so you're compressing, and what are you compressing? Solid, liquid, or gas? Yeah. Well, yeah. Eventually, yeah. So you're jumping ahead. So gas to compressed gas, and then Celicia, what happens from O to P?
It starts kind of it evolves subliming because it's going to solid.
Yeah. So it's the opposite of subliming. I don't exactly know what, but I would call it maybe deposition. So the gas is turning to a solid directly. It bothers me to say condensation for a solid, so I'm trying to think what would be the solid version of condensation. So I'd say deposition. So it's kind of like chemical deposition. You're compressing the gas, and all of a sudden it starts to drop out on all the surfaces and make a solid. Okay, Madri, from P to Q.
So pressure is increasing
Mm-hmm.
and the volume is changing.
Yeah, decreasing slightly. Yeah, so we went straight from gas. We deposited all of that gas as a solid, and now our piston is all the way in, and it's pushing on the solid and trying to make it smaller, and it requires a lot of pressure to do that. Has everybody been okay following me without drawing on the board a piston? So changing this volume is a great way for me to think about a piston. It's just a pushing on the substance, changing the volume. And how much pressure is needed to do that is the y-axis, the pressure. And that's what you do for an isotherm. That would be isothermal compression. If we run these backwards, it's isothermal expansion. So we would be pulling on the piston. And you say, well, how do we, many times when things expand, they cool. So how would we keep it isothermal? When you pull on that piston, it has a tendency to cool, so you just put it in a water bath or some kind of thermal bath so that the energy goes in. Whatever energy, of expansion is lost to expansion, you're putting back in by the isothermal bath that you put it in. So you can hold the temperature constant if you put it in thermal contact with an object. So this may be your system that you have, but the surroundings are supplying the energy or taking away the energy. If you compress a gas and it wants to heat up, you have it in thermal contact with something that keeps it at the same temperature. And so you compress that gas and energy leaves the system to the surroundings so that it can stay the same temperature.
Or if it's in a computer system, you can just tell it to sit.
Yeah, that's right. Yeah, it's very easy to do electronically. Yeah. So that's the main thing. This Gibbs energy. These are Gibbs energy lines. Let's finish with this. And so there's. Let me just go back. You've heard probably in your previous PChem experience the term chemical potential. Okay, we did a lot with chemical potential. When we're talking about spontaneous reactions, it's nice to think of a ball on a hill. A ball up the top of a hill has a high potential energy. And if you get it rolling, it turns that potential energy into kinetic energy. Okay? That's where this term potential comes from. This Gibbs energy that a molecule has, or any kind of system has, is chemical energy. It's potential also. So it's chemical potential. If you have high energy molecules, they have a high chemical potential. They can react, and you can have spontaneous reactions. If you have something that's really low in energy, it's got a low chemical potential. It's going to be great as a product, but not so great as a reactant. Okay, so your really high energy things are going to be your good reactants. They're going to get together and spontaneously react, and so they have high chemical potential. Basically the molar Gibbs energy is your chemical potential. So this sort of a connection to the terminology that you've had in the past, PChem classes. Chemical potential is just the molar Gibbs energy of a substance. Okay. Now, at a phase, when you're at equilibrium in a phase change, you've matched the chemical potential for solid and liquid, because the solid's becoming a liquid and the liquid's becoming a solid. And so since they're changing both directions, the Gibbs energy delta is 0. Okay, it's spontaneous in the forward and reverse reaction. So the Gibbs energy of the solid phase and the liquid phase are the same. And so when you're at equilibrium between two phases, you have the same chemical potential in phase 1 and phase 2. So that's the situation here where these intersect. So if you were to plot with respect to temperature, the chemical potential or the Gibbs free energy for that solid, there would be a place where that solid has a higher Gibbs energy than the liquid. And it would be spontaneous for that solid to become a liquid, because delta G's, spontaneous delta G's are negative. And so you're going to follow the lowest possible delta G, because if you're at a higher delta G, it'll have a phase transition to get to the lower one. When those intersect, they're equal, and so delta G equals 0 at that point. But like here, if I had a liquid and I cooled it below its freezing point, I could have a super cooled liquid. And then it's really just a kinetic effect. It hasn't had anything nucleate the solid formation. You scratch the side of the beaker or you drop in a seed crystal, and now you're able to facilitate that spontaneous freezing. And so you can supercool a liquid and it'll spontaneously freeze, and it'll give off that energy, and it'll be exergonic. You can also superheat a liquid. You could get a liquid that's above the boiling point, and kinetically it just hasn't formed any bubbles and hasn't released that energy. Okay, and that can happen in a microwave oven. If you don't have the little rotating tray that vibrates and shakes your beaker. It can also happen in a round bottom flask if you don't have boiling chips, and it can bump. Okay, so you can have a super heated fluid that will violently boil, because if it's above the Gibbs energy of the gas, it can violently drop down and release quite a bit of force in a small amount of time. So that's where bumping comes from. You can have superheated things in the microwave. If you don't, the first microwaves that came out didn't have the carousel that rotated, and it would just bump on you and blow up. Sometimes, like a glass or you're boiling water for tea or something, you have a superheated cup of tea, you go and grab the handle and it all boils at once and splashes on your hand. So a lot of people got hurt, so then they put in the carousels. It also distributes the heat too as you go along, but it also vibrates the flask so you don't get superheating. Funny story, in elementary school, my buddy, like the first microwaves were showing up into people's houses, and my friend had one, we didn't have one, so that was cool. He had a microwave, all right? He stuck an egg in there and just turned it on for several minutes. We were in the other room, no kidding, playing Space Invaders, like that was. So we're playing Space Invaders, have you seen Space Invaders? Yeah. And we hear him in there, and we hear the microwave open up, and he goes, "Oh, it didn't do anything." And then we hear, "Ah!" The egg exploded. And he had little cooked egg bits on his face. And they looked like little dead skin pieces. Like he picked them off, and he had these little red blisters. It looked like he had chicken pox. Of course, what do elementary school boys do when their friends hurt? We laughed so hard at that, it was great. So anyway, that egg was superheated, and it exploded right there. So when you follow these equilibrium lines, think about the chemical potential of those phases here. You can see that as well here, color-coded, here's the chemical potential or Gibbs free energy versus temperature, and everywhere those lines mark, you see these different phases. Now, it's conceivable that the solid line would be so low that it would cross the gas line and never have the liquid line, and that's what's going on down here. So the liquid is never below the solid or the gas. The chemical potential for the liquid is up here, but the solid and the gas cross below it. And so that's when you have this solid gas equilibrium. And then that's a good place to stop.